So in this session, we're going to look at the nonlinear dynamics that are associated with the energy balance in a CSTR. So when we talk about nonlinear dynamics, we are referring to the changes in time in terms of our state variables in the reactor. So if we think about our reactor, there are a few basic variables that can be used to represent its state. So the concentration and the temperature, those have been the primary variables. One could also think about the pressure and perhaps even the level, if it's a liquid phase reactor, things like that. So those are all variables that reflect the state of that reactor, and the values of those variables may change with time. And as we've seen, we can write material and energy balances, and we can find the rate of change of such variables in time. So generally speaking, equations of this form represent our reactor. And when we talk about the nonlinear dynamics, we are interested in what these equations tell us about the behavior of the system over time. So as much as we can derive our material and energy and momentum balances, and we think of those in quite physical terms, the physics of the problem, they describe the physics of the problem, we can still regard those as equations that can be analyzed and understood in terms of the general behavior that certain types of equations exhibit. In other words, once we know an equation has a particular form, then we can identify that the system will behave in particular ways. So that's where we can enumerate different types of dynamics that can be observed for the system. And here's another example. This is just showing us that this applies not just to the types of equations that we are quite familiar with, right? In chemical engineering, most of our balances appear in this form. If you look in mechanical engineering, where we are more interested in perhaps oscillations and tensions and things like that, then we may have second order time derivatives. And this is just pointing out that we can always convert a second order derivative into two first order derivatives. And here's a quick example towards this. We can see we've got an equation, it's second order in time, and we are proposing here the creation of two new variables, x1 and x2. So in this equation, we have the single variable x, the single dependent variable x, but now we are saying instead of just x, let's break that down into two new variables. So we'll create x1, which is nothing but x itself, right? It seems a bit silly, just a relabeling, but anyway, we create x1, and we also create x2. And x2 is nothing but the derivative of x. So dx dt is x2. And you could also say then clearly x2 equals dx1 dt. So anyway, we can create these two variables. There's nothing to prevent us creating such variables. And so we can say the first relationship is simply from our definition. We have simply defined x2 to be dx dt. Therefore, dx dt, we know that's the same as dx1 dt. So that's nothing but equal to x2. So this is purely from the definition of x2. Then we can look at our balance here. So our original equation, where we don't like this second order derivative, we can drop the order quite easily because now we have this x2. And so if we differentiate x2, if we take dx2 dt, then that's going to be a derivative of the right-hand side. So it's going to be ddt of ddtx, which is nothing but d2x dt squared. So the second derivative of x2, right, the derivative of x2 here is going to be the same as the left-hand side here. So now we have something that looks like a first order ODE. If you follow the rest of this, you've got kx, which we write as kx1, and then you've got m times dx dt. So we know that's an x2. So see, we've now converted a single second order derivative, a single second order equation into two first order ODEs, right? And we do know how to solve these. So we have talked maybe a bit more in second year in the maths course, but also in the fundamentals course. We had outlined ways of solving systems of systems of first order ODEs. They are coupled because the rate of change of x1 depends on x2, and the rate of change of x2 does depend on x1. So these equations are coupled. So this is just pointing out as an example that that even in cases that appear to have just one state, sometimes it's equivalent to cases where we have two states. And in our case, we know that we have a material balance and an energy balance. And so our interest is in the relationship between conversion and temperature. And we had already looked at such relationships. We did an entire design of a reactor around the plane X and T. But let's now look for the dynamics. What are all the possible events that could happen in a reactor in terms of X and T? So towards that, let's define first some concepts in dynamics. So you've met steady state and unsteady state. You're quite familiar with that. But a steady state it is more sophisticated than that. A steady state may be influenced by other factors. So a steady state, as much as we think of a steady state as a state that our system is always moving towards, and we saw a bit of that. We saw the equilibrium in a reactor, that we said that nature was always trying to go towards equilibrium. But it's not always the case that an equilibrium or a steady state is stable in that way. So it's not always the case that nature is going towards a steady state. And towards that, let's think about this very simple example here. Let's say we have a ball at some position, and then we have a valley here and a hill here and another valley there. And so if we think about giving a kick to this ball, then that ball might roll down here and encounter this valley. So it's going to fall, and then we can imagine with its momentum that it's picked up from the kick and from its travels here, it will rise for a bit, but then it will fall back, and it may bounce back and forth a bit, but eventually it will come to rest here. So we can imagine then that this is a steady state. We can see this is going to be a steady state, and we will think of this as a stable steady state. So when we say stable, we mean that that if we are at the steady state, and if there is a small disturbance to that steady state, so let's say we come in and we just give the ball a tap or something like that, the ball may move a little, but it will come back to the steady state here. So that is what we call a stable steady state, or if you like, a locally stable steady state. And we'll come back to why I'm saying locally just now. And it's a similar situation here, right, in what we've labeled Valley A. So if we kick the ball hard enough and it passes Hill B and falls into Valley A, then again, if we apply a small disturbance, if we give it a small kick around here, then it will rise a bit, but it will fall back into this valley. So these we can term two stable steady states, right? Once we are in the steady state, we tend to stay there. So that's a stable. Whereas if, let's say, we walked the ball to the top of Hill B and we placed it there, then you can imagine that that there will be a point where that ball can sit. And so that ball may reach a steady state up here. So the ball may be steady if we place it carefully enough up here. But also, if we give a small kick to this ball, then that ball is going to fall away from the steady state and enter a different steady state. So that's the notion that, well, those are one of the concepts in nonlinear dynamics, the multiplicity of available steady states, that the state of your system, right? The state of this ball is its position. So it's X and Y coordinates in this plane. So that state of that ball, it actually has three available steady states here. And these three steady states do behave differently. We have stable steady states here, and we have unstable steady states there. And so wherever we start will determine which steady state we fall into. And we could even see this unstable steady state as a kind of separation point where it decides if we start to the left of this point, then that's the available steady state. If we start to the right, then that's the available steady state. So those are concepts that we'll see just now also apply in our energy balance. Okay, so that's the concept. So we want to know, does such a thing exist in our, let's say, our CSTR? And towards that, of course, we would have to go back to our balances. And looking at the mass balance first, we know that's our CSTR mass balance, and we can rewrite it a little more conveniently. And if we go back to our energy balance as well, we know it has this form. So if you go and look up the expression we developed for the energy balance, we get the exact same thing as here. And this is, of course, the version of the energy balance where we do add or remove heat from the system. So if you see this, there's heat exchange with the jacket or cooling coil or something like that. So this is the non-adiabatic version of the energy balance, right? The rest of this, we know that the change in temperature of the species, that must be balanced by the reaction heat and all of that. But we are adding heat as well. So anyway, we've got our material and energy balance. And towards deriving the view that we are talking about here, the first thing we'll do is substitute for this part of the energy balance. So we can say, well, FA naught X, I don't want too many variables here. So instead of another X, let's try and get rid of the X's. And we know we can just use the material balance. So we can use this version of the material balance. So for FA naught X, we can just substitute this by RAV. And so that's an updated view of this energy balance. And then we also introduce this definition. So we just create a variable kappa, which is UA over FA naught sum theta I CPI. And if you look at this expression, let's say we just extract this sum over CPI. So let's say we extract that as a factor from the square brackets here. So if we write that out here, so you can see it down here, right? We've extracted the theta I CPI term from the square brackets. So that's fine for the first term. That's we know we have to multiply that. So the first term can stay as it is. However, for the second term, when we extract a theta I CPI, of course, this term doesn't have theta I CPI. So we're going to have to write this part of the term with dividing out theta I CPI. So if we divide theta I CPI, then we can extract this factor from the brackets here. So we've just written this factor on the outside, and that means we have to have U times A divided by theta I CPI times FA naught. And now we've defined this kappa to be that same factor. So we can rewrite this as kappa times T minus TA, right? So the T minus TA stays the same over here. So that gives the form that we want to look at. Okay, now that is our energy balance. And if we look at this balance and think about the meaning of the terms here, we can see on this side of the equation, the heat of reaction and the reaction rate. So this is the energy, if you like, the thermal energy that the reaction evolves, right? And I'm trying to avoid the term generate. And unfortunately, we do use a big G for generate and an R for remove. But of course, we shouldn't be talking about generating heat and all that. But anyway, this term actually means that whatever energy that we are able to convert some of our chemical potential energy into a thermal energy. So that's how we interpret the right-hand side. This has to do with the amount of heat that the reaction is giving off here, right? So that's the left-hand side. On the other hand, on the right-hand side, we can see this is all about heat exchange between the jacket and the reactor, right? There's a bit about the inlet feed and so on. And of course, this inlet feed and the fact that there's a difference in temperature between the inlet and the actual reactor temperature, and then that's balanced by the heat being added. So all this is about how much heat are we removing from the system. So how much heat are we generating in the reaction versus how much heat are we removing? And of course, in our CSTR, we like steady states. So we are interested in the point where these two are equal, right? We don't tend to like the case where we aren't removing enough heat. So imagine that we are not removing enough heat, then that means the reaction is oversupplying heat, and that means the temperature will rise and maybe the reactor will fail as a result. So with all that, anyway, if we are at steady state in temperature, these two will be equal, right? So that is how we read each side of the equation, and then we can then define the left-hand side and right-hand side. We can call G the heat generated by the reaction, as we said. So that's simply the left-hand side there. And then in terms of the right-hand side, the heat removed by the cooling equipment, that's what we've derived and found there. So that's what we have. And if we look at this equation, this is pretty straightforward, right? This R of T, we would like to plot how much heat is removed, right? R does have units of energy. I think it's energy per time. But R does have units of energy, basically. And we would like to know how much heat is removed as we consider different temperatures in that reactor. So RT is shown here. And we can see that everything here is a constant, right? Think about the pure A case. Quite often this collapses simply to CPA. And then this kappa, when we look at kappa, our definition for kappa here, it's the thermal characteristics of the jacket. So the overall heat transfer coefficient, the available area, the feed flow rate, and then the heat capacities. So all this is quite constant. It is influenced by what we are using at the inlet point, but assuming that's all constant, then kappa is a constant. So when we look at this equation, this is a constant and T is our variable, right? So that's the independent variable. T inlet, of course, we are regarding that as another fixed thing. So we are feeding to the reactor at a fixed temperature. And then we know kappa is constant, as we said before, and the jacket temperature is also, we'll regard that as a constant. So now we can see a constant times something which has our variable, and everything else is constant. So this is basically y equals mx plus c, right? So this R line is expected to be a nice straight line. So that's what we expect there. So we'll park that expectation and come back to it when we actually draw it. Now let's look at the heat generation term here. So we said we have RAV over FA naught and the heat of reaction. And we said RAV equals FA naught. So if we are dividing by FA naught, then we've got the X here. So that's our heat of generation term. Now, if we think back to our material balance, if we have a first order reaction, then our reaction rate is kCa. right? So first order reaction means A is being consumed proportional to the reaction rate. I mean, the rate of reaction is proportional to the concentration of A. So that's a simple first order reaction. And of course, the concentration of A can be written as Ca naught times 1 minus X. And if we look at this, we've got Fa naught over Ca naught. So your molar flow rate divided by your molar concentration. That ratio must be the volumetric flow rate. So of course, our volumetric flow rate, we have been using the symbol Q. I think we used uppercase Q. So for some reason, I was using this. But anyway, just read this, please, as a volumetric flow rate. So we've got a volume and a volumetric flow rate here. So of course, we like to go and divide by that and get a nice tau here. So if we do that, then we'll have tau equals x over k times 1 minus x. And then if we make x the subject of the formula, then we can see we'll get this expression. So that's how x is varying with k and tau. And if we just think about this, tau is the space-time. How much time do we spend reacting there? So if our reactor is very tiny and we spend very little time in there, so if tau is very small, then it's a small number divided by 1 plus the small number. So it's approximately 0 over 1. So that's a 0. So it's what we expect. If tau is very small, we don't expect much conversion. So once more, if tau is very small, then we've got basically 0 in the numerator divided by 1 in the denominator, which is overall 0. So for a small tau, we get close to 0. If, of course, tau is very large, so if we are spending lots of time in the reactor, then this number in the denominator, this tau times k, is going to be much greater than 1. And so this equation becomes approximately tau times k over tau times k, right? Because tau k is much more than 1, so we can just ignore the 1. And if we do that, then the tau k's can cancel, and this thing becomes a 1. So for very large values of tau, x is about 1. And that's what we expect. If we give the system a long time to react, then we get a complete conversion. Equivalently, if our k is very large, in other words, if our reaction rate constant is very large, that means the reaction is very fast. And so we can see, again, if k is very large, then we can forget the 1, and this becomes a tau k over tau k, which is 1. So conversion goes close to 1 when k is very large. By the same token is k. If k is very small, then you've got 0 divided by 1 plus 0, which is 0. So it gives us all the expected results there. Okay, so that's what we have in terms of our, that's what we expect here. But that was just by the by. What we actually want from this is, now we've written it in terms of these k's, and we know we have the nice Arrhenius expression for k. So if we substitute that in there, then we've managed to get rid of all the unknowns. So we didn't know what the reaction rate was. Well, that was the only thing, right? We assume we know the heat of reaction, the inlet flow rate, and the volume. So just the reaction rate we didn't know. But now we want a nice temperature function. And we found a way to convert this using our energy balance. We found this is equal to x, and we've shown x is equal to this. So this is now the nice temperature function that we were looking for, because these k's are temperature dependent. So we have the generation term, we have that now explicitly as a temperature function. All right, so now we have the two things we were looking for. We have r as a function of t, so we can plot this, and we have g as a function of t. We did say r is a nice straight line. It looks complicated with our new kappa and all that, but by the end of the day, if we read this carefully, we can see this is nothing but y equals mx plus C, right? So that's a straight line. R is just a straight line. On the other hand, here we have an exponential of 1 over t minus, and so this is quite nonlinear. Each k here is nonlinear, and there's this 1 plus down here. So this thing is going to be quite nonlinear. However, we have talked about the extreme cases. So we did talk about extreme values of k, very large and very small values of k. And equivalently, we know that when t is very small, then k is very small. When t is very large, then k is very large. So for G, I'm just going to skip here. So for G, we expect that we'll get something close to 0 here. And then as t goes up, it will saturate to some other value. So we do expect to see something of this shape, right? So for small values of t, k is very small, so x is very small, so we're down here. For large values of temperature, k is very large, so x is close to 1, and then it doesn't increase beyond the 1. And only x is going to change. If we look at this expression, our heat of reaction, if we take that as approximately constant, then everything is constant except for these k's here. So we do expect that it's going to take this form. It's from a small value to a large value, and we get that change like that. So if you look at these graphs, you say, well, this is pretty boring because you've got just a straight line here, and then find g of t. We thought it was very nonlinear, and it is nonlinear, but at the same time, it's not kind of shockingly nonlinear. It looks like this, right? It's the sigmoid, which we know is associated with second order type things. But anyway, that's our g of t. So why do we get interesting dynamics behavior with this? So let's keep going. So here, this is just a comment. Yeah, as you go to large values of temperature, x becomes 1. And so, of course, where is it here? When for large values of t, x becomes 1 and g becomes the heat of reaction. So as it turns out, we can very quickly draw g of t as well. We know the upper asymptotes. It's nothing but the heat of reaction. And then we could just plot 1 or 2 points here and then generate a sigmoid. So we can draw this easily. And then that's just a comment. We can see as tau increases, then g sharpens. So it might slowly develop that sigmoid shape, or as we increase tau, it becomes sharper and sharper. So anyway, we can plot both these. Then we know R is a straight line, but the gradient here, so it's the 1 plus kappa. So as kappa increases, the gradient does increase as well. And as we change the inlet temperature, we can see that's going to change it's going to change the intercept. So that's how R changes. So we are interested in the case where G equals R, because that's our steady state. And let's think about what steady states are available for different inlet temperatures. So remember we said R changes its intercept as we change the inlet temperature. So for now, we're not going to change kappa. Let's just change the inlet temperature here. So if you start with this inlet temperature, and if your kappa was such that we had this gradient, then we can see the R line will equal the G line at this point, right? So once more, we are plotting G and R, right? Remember, those are just terms on either side of the equation. That was the left-hand side, that was the right-hand side. And we know we have both of them as functions of temperature. So we let X be temperature, and we draw both graphs then. So we have the straight lines for R, and we have this curved line for G. As we change the inlet temperature, we will get different R lines. We know that G is not influenced by the inlet temperature. Excuse me. So this first inlet temperature has just one steady state here. And we can see that if we start with this temperature. Let's imagine the case where we are at the unsteady state operation. So in our CSTR, we start off with this inlet temperature. So the whole reactor is initially at this temperature. Then let's think about how our temperature is going to change. So just a second, I need to clear my throat there. So let's think about what happens. We start with a temperature down here. And let's think about the relative positions of these two curves, right? That's the reason we draw G and R on the same graph, because we can easily see what's going to happen, right? So at this point, TI6, G is greater than R, right? Here's the R line, here's the G line. So G, we know, is generating heat in the reactor, right? So thermal energy is increasing as chemical potential energy goes down and thermal energy goes up. Basically, it means the temperature will tend to go up. So wherever this G line is above the R line, we are going to increase in temperature. So here at TI6, we can see the G line is greater than the R line. So this means in this region, the temperature is going to rise. Another way to think of this is let's make a quick document for ourselves. So we can think of it this way. We can say, we know our energy balance looks like this. So we can say at steady state, we have that G of T equals R of T. But if it's not at steady state, then we can write at least something like this. We can say dt is going to be proportional to, so I guess the alpha kind of looks like a proportional symbol. So it's going to be proportional to G of T minus R of T. So looking at this, our understanding here, right? Remember, we saw in our energy balance, this is the heat generated by the reaction, and this was the heat removed by the jacket. So that's equal at steady state. But if we are not at steady state, then we can imagine that the temperature will tend to change, and we put G in this position. We will say it's plus in G because this tends to raise the temperature, especially, well, if it's an exothermic reaction, this is going to raise the temperature. And this is to remove heat, so minus R. So G will tend to cause temperature to rise, R will tend to cause temperature to drop. And this means that if we can see that G is more than R, the temperature is going to tend to go up. So let's think about that in the context of what we drew here. So down here, we said G is greater than R, so the temperature will tend to rise. So that means if we start here, the temperature is going up here. So temperature is rising, so we are moving to the right here. And we can see as we move in this direction, yes, our G and, well, our R is increasing here. Our G value is also increasing. Let's think about a point here. So we started here, the reactor temperature tended to rise, and so it's moved off to the right here. And we can see at some point here, the difference is even greater. So it's not just that it's larger, it's larger, right? G is larger, the amount of heat being given off is larger, and it's growing, it's getting even larger. So by here, we have the maximum difference. And then we start to reach a stage where they start to converge. So G, we've now reacted as much as we possibly can. The CSTR is saturated with product and the reaction is not really happening. So we stop generating heat when the conversion gets high enough. On the other hand, as the temperature is rising, R is also rising. So we are removing more and more heat. So R doesn't get affected by the reactant running out, right? So we can think of it that way. The G line settles out because it's running out of reactant here. The R line is not dependent on the reactant, and so that just keeps rising. And so up here, we reach a stage where G equals R. And here we can see that's our steady state. So even if we start down here, we know this is the inlet temperature, but even if the entire reactor was this temperature as well, then the temperature in the reactor would rise until it reached this stage. And we can see here, if the temperature were to continue to rise, then the heat removed would become greater than the heat generated. And so we would, on balance, be removing more heat here. And so the system would tend to come back to this point. And by the same token, if for whatever reason the temperature dropped in the reactor, then we can see the heat generated would tend to restore that the heat generated would be more than the heat removed. And so the system would then rise in temperature back to this point. So this point is a stable, steady state, right? We have a point where once we reach it, if the temperature rises, because of the increased cooling, the system will go back to that point. Or if the temperature drops, then the higher heat generated would cause us to fall back to that point. So this is quite a stable, steady state. Okay, and that's the one steady state that's available at TI6. We won't talk about TI5 just yet. Let's look at TI4. Now the situation, excuse me, the situation is a bit different here. When we start at TI4, yes, the heat generated is more than the heat removed, so the temperature does rise, but then quickly we get an intersection where the two are equal. If the temperature goes a little above this value, then the heat removed is greater than the heat generated. So we'll fall back to this point. And then down here, we just said if the temperature goes down, then it tends to push back to this point. So this point is also a stable, steady state. Just like we had a stable, steady state at 11, we can see that 0.7 is a stable, steady state as well. But now let's say we somehow force the reactor temperature to go all the way up to 0.8. Now we can see here 0.8 does have an intersection. So we have G equal R at 0.8. But the situation here is quite different, right? If we reach 0.8 and then the temperature increased slightly, then you can see that at 0.8, if the temperature increases, then we are sitting somewhere here in terms of temperature where G is greater than R. So at 0.8, we are tending to run away to a different temperature. So the moment we go slightly above this temperature at 0.8, the system will run away to a different temperature. And also, if we look below 0.8, if the temperature drops even slightly, then we have that the removal rate, right? The straight line is the heat removal rate. That becomes greater than the heat generated rate. And so we would fall down back to the steady state. So 8 is what we call an unstable steady state. It is a steady state. We do have G and R equal, but the moment we deviate from it slightly, we tend to fall away from it. If the temperature drops a little, it's going to fall down to steady state 7. If the temperature rises a little, it's going to fall up to steady state 9, right? And if you work through where is G more than R and all that, you'll see 9 is a stable steady state. So you can say we have a branch of stable steady states here and another branch of stable steady states here. Here in the middle, we have a branch of unstable steady states. And we also do have a region where there's just one steady state. So remember when we started out, we had that we would just, for temperatures starting in this region, we had just one steady state. And we can see if we have a greater inlet temperature, again, we will have just one steady state. So there is a region, which is TI5, where we transition from having 3 available steady states to just 1 available steady state. So again, if we start just to the left of TI5, and we are, let's say, at TI4, we can see we have available 3 steady states, 7, 8, and 9. One of those is unstable, but it's still a steady state. 2 of those are stable. So it depends which side of 8. We could think of 8 as a like a criterion, or as a distinguishing point where just to the left, then we have to only fall to the steady state. Just to the right, and we only fall to the steady state. Because out here, we can also think about points out here. The moment we are out here, the removal rate is greater than the generation rate. So we will always fall back to this branch here. So we have 3 steady states available here. And we have 1 stable steady state, or we have 1 steady state. Let's just say steady state. We have 1 steady state here. We can see TI5 is kind of a special, it's a special temperature, because when we are just to the left of that, we have 3 steady states. And when we are just to the right of it, we have 1 steady state. So we call temperatures like TI5 a bifurcation point. So bifurcation in Greek, it means, so bifurcate means to split in 2. So you were traveling down a path which was just a single path, and then you reached a point where the path split in 2. So your bifurcation is here. And in fact, in this case, we get 3 steady states, but we still keep that name bifurcation. We even use it if it splits into more points. So anyway, it's a bifurcation point. This is not the point. The point is here, right? The inlet temperature of this value. That's a bifurcation point. And in chemical engineering, we give it a special name. We say this is the ignition point. So why ignition? Right? Imagine that we were operating at temperatures down here. So we only saw the reactor go and settle down to these temperatures. Then suddenly we exceeded this inlet temperature, and the system ran away to this much higher temperature. So in a sense, it ignited, right? So this is a kind of ignition temperature. Just past this temperature, the system flies away to a higher steady state, a higher temperature. And by the same token, there is another bifurcation at point 3. So point 3, which is associated with inlet temperature 2, we can see just to the left of temperature TI2, inlet temperature 2, just to the left, we only have 1 steady state available, right? So if we start down here, R is less than G, so the system is going to push up. And so that's 1 steady state. If we exceed the temperature, then here R is greater than G, and then the system gets pushed back down there. So, and if you follow this line all the way through, there's no other feature there. So if you start out here, and that is your inlet temperature, so you can start as high as you want, R is always going to be more than G. And so you will always push along down here and fall into the steady state. So just to the left of TI2, all those inlet temperatures force us down to only this temperature. And so between Ti2 and Ti5, we have 3 steady states. From greater than Ti5, we have only 1 steady state. And for less than Ti2, we only have 1 steady state. We call Ti2 the extinction temperature. So here, just when we were operating at inlet temperatures just above Ti2, we always had available this higher steady state. Then when we applied a temperature slightly below Ti2, then suddenly we couldn't operate at this high temperature anymore. We could only operate down here. So you see, that exposes then the critical temperatures that we want to operate at, right? It might well be the case that we want to operate at these nice high temperatures where we have high reaction rates. Then we need to know that there do exist these unstable steady states, these repulsors, which we must cross. We have to force the system always to be more than this temperature. Then we'll operate stably here. But if we don't do that, we're going to fall down here, and we might not want the temperatures down here and the reaction rates down here. And similarly, if let's say the material of construction has a constraint like that, so let's say we couldn't exceed this temperature, right? The material of the reactor couldn't withstand temperatures beyond this point, then we definitely don't want to exceed this. We definitely can't afford to go and operate past this inlet temperature. So that's how critical it is. Even though the inlet state, we've thought of that as just another constant that we had to get hold of. It turns out that if we don't choose these values very carefully, we can end up operating in a region that we might not intend to. And there are critical regions, right? Ti2 and Ti5, where the system can switch very suddenly. So we thought we were operating peacefully down here, and then the inlet temperature rose slightly, and suddenly the system ran away up here. And these are all real cases, right? In real reaction engineering, this is an issue that has to be designed around quite carefully. So that's our bifurcation, and that's how that is the type of nonlinear dynamic that can influence our system and our design, and it features in our control strategies and so on, right? So we'll be working through problems like that in the tutorial tomorrow. Okay, I'll see you then.